Here's problem 8.6. A 2 kilogram block sliding on a frictionless horizontal surface is attached to one end of a horizontal spring constant 600 newtons per meter, which has its other end fixed. The speed of the block when the spring is extended 20 centimeters is equal to 3 meters per second. What is the maximum speed of the block as it oscillates? All right, let's see what we have here. We have a block attached to a spring, and the spring has been extended a distance x equal to 20 centimeters, 0.2 meters. So here's our block, and it's moving at that point as well. It's moving with a velocity of 3 meters per second. It doesn't really matter which direction it's moving, because it's going to have kinetic energy and potential energy of the spring being extended, but it really doesn't matter whether we draw this velocity to the right or to the left, actually. So I'm just going to draw it to the left. Velocity is equal to 3 meters per second. Let's call this point A, so this would be the velocity at point A. In other words, this point will be point A, and then when we finally reach our equilibrium point, that's going to be point B. K constant is 600. So if we were to look at this just a moment later, there'll be some point when the block is at point B, the spring is no longer stretched, and that point the velocity will be maximum. Why? Because all the potential energy that was in the spring when it was stretched is now gone into kinetic energy, and there's kinetic energy will be at its maximum value because there's no more energy for us to obtain. So this will be our maximum possible speed occurring at equilibrium when x is equal to 0. So x at B equal to 0. This would be x at A. Okay, so that's our problem right there. We have the one equation to rule them all: kinetic energy at A plus potential energy at A plus any work done along the way will equal to kinetic energy at B plus the potential energy at B. We have no work done along the way in this problem because the spring, even though it's doing work, is a conservative force, so we've accounted for it by potential energy. So we don't have any other external force to worry about. We do have kinetic energy at A, so that's 1/2 mass velocity at A squared. We have potential energy at A, but not gravitationally, because we're going to define our plane as being our zero height. So we only have a 1/2 kx squared at point A. That's equal to our kinetic energy at B, which is 1/2 mass times velocity at B squared. And our potential energy at B is going to be 0 because the spring is no longer stretched or extended, and we have a gravitational potential energy of 0 because our height is 0. So that's all we have. So let's solve this for our velocity at point B. So we have 1/2 mass times velocity at B squared is 1/2 mass velocity at A squared plus 1/2 kx squared. Multiply both sides by 2, divide by the mass, take the square root. Velocity at B is going to equal mass times velocity at A squared plus kx squared, divide by the mass, square root. So that is going to be 2 times the velocity at A, which is 3 squared, plus k, which is 600, times x, which is 0.2 squared, divided by 2, all that square root. And that gives us, so that's the square root of 21, or 4.58 meters per second. So that is our velocity at point B, our maximum velocity occurring at the equilibrium point of the spring, 4.58 meters per second. You could use calculus to set up your equation and then maximize the equation, and you would prove that your maximum value should occur when x is equal to 0. But our intuition is good enough. 4.58 meters per second.